Good morning, everyone. I am Riccardo Capuzzo, and today I will present our work, creating embeddings of heterogeneous relational datasets for data integration tasks. With data integration, we describe the problem of combining data coming from different and heterogeneous sources to provide a unified view. A simple example of this is shown here. Stacks of rectangles represent groups of documents which should be combined in a single source, like the super table on the right. In our work, we will focus on two specific cases of this, schema matching and entity resolution. To do so, we chose to use embeddings. In short, embeddings are a data representation technique that works by assigning to entities a real-valued vector that identifies a point in a highly dimensional vector space. Points in vector spaces enjoy some geometric properties that can be applied to categorical data, such as numerical distances. Little work was conducted on how to perform data integration using embeddings, with most solutions being highly task-specific. Prior results usually fall in one of two camps, pre-trained and local. Pre-trained approaches rely on embeddings that were trained using general-purpose corpora, such as fast text on Wikipedia. These approaches have two main issues. Out-of-vocabulary words will not be properly represented and in-vocabulary terms may lead to unexpected results due to unwanted background information. On the other hand, local embeddings are trained on the data at hand, so the out-of-vocabulary issue does not occur. However, it is not trivial to find an effective way of creating such embeddings, with much of prior work naively treating tuples as sentences. We propose one such effective training technique as one of our major contributions. The core of our work is EMD, which is shorthand for embeddings for data integration. EMD is an unsupervised system that performs different data integration tasks. These include entity resolution and schema matching. EMD embeddings can also be fed to other algorithms to perform further operations on. The code of EMD is available to be tested at the link shown below. This slide shows the workflow of EMD. The system takes as input relational tables that undergo some pre-processing. The pre-processing step has the objective of increasing the overlap between datasets to be integrated through some transformations such as removing caps, rounding numbers, and removing punctuation. The pre-processing step includes the concatenation of different datasets in one. This data is then fed to the graph contraction algorithm to build the graph shown in the middle of the slide. This graph representation allows to retain most of the information while remaining more compact than other solutions. To describe the graph to the embeddings algorithm, we build a training corpus using random walks. Note that it is not necessary to use the embeddings algorithm included in MD to build the final embeddings. It is possible to use graph embeddings algorithms such as Node2Vec or HAR to create the final embeddings. Either way, we will have our training vector spaces. To represent relational tables, we chose a graph structure like the one on the right, with each node belonging to one of three classes, either token nodes, record nodes, or column nodes, so RIDs or column IDs. Token nodes describe unique values in a concatenated dataset. Each RID node represents a tuple in the dataset, so for example, R1 will represent tuple 1, and each column ID represents an attribute in a table. So title will represent the attribute title. Quite simple. This means that both column IDs and record IDs receive their embeddings organically from the algorithm without needing to rely on methods such as averaging or summing or concatenating the vectors in a tuple. As I mentioned, to increase the overlap between datasets, cell values with the same syntax are collapsed in a single node. Multi-word tokens may cause some issues, however. For example, consider the simple case of saving private trial in the top, or the more problematic example reported at the bottom of the slide. To handle those cases, we tested three strategies. The first is MDS, which assigns a single node to each unique cell value. So saving private trial will be assigned on a single node, regardless of how many words it may contain. So even ClickArt 950,000, etc. you see at the bottom will all be assigned a single node. MDF instead will create a node for each word in a token And MDO is an optimization made specifically for data integration, and it works by applying MDS if the token is present in both datasets to integrate, and MDF otherwise. Finally, the strategy you see on the right, MDOF, is a new technique we developed recently, which creates a node for the multi-word token and one for each word in the token. For this, we do not have any results in the paper. However, it actually outperforms the 3 previous results. Now, once the graph has been prepared, random walks are used to traverse it and to build the training corpus. The random walks are a proxy to describe the graph to the embeddings training algorithm. It is possible to improve the corpus by using weighted random walks or sentences generated using other means. Sentences should include record IDs and column IDs, so the embedding algorithm is aware of their existence. The random walks make up the training corpus that is passed to an embeddings algorithm. As one can expect, the hyperparameters used in training phase have a large effect on the final embeddings quality. It is also possible to use any training algorithm that can take as input the sentences we are supplying. As for the task that we conducted, the first thing that we tested was observing if the embeddings were able to represent some of the relationship intrinsic in the starting relational table. And we devised a selection of tests to do so. We implemented 3 of them: match attribute, match row, and match concept. Some simple examples are shown here, and more detail is in the full paper. For match attribute, we want to recognize an actor among movies. For match row, we corrupt a tuple by introducing the wrong value in one of the fields and check if the algorithm can correctly point it out. For match concept, we observe if, for example, Quentin Tarantino, the director Quentin Tarantino, is more closely related to his movies, Pulp Fiction, Django Unchained, or Reservoir Dogs, then those movies are related to other movies that are not by Tarantino, such as Titanic. The results for this are, of course, will be reported in the paper. For the schema matching task, we are given tables that contain similar content with misaligned columns, which try to reconstruct a combined view of the relations. For this, we use a simple unsupervised algorithm that relies on bidirectional relations between columns to perform the matching. The last task we consider is entity resolution, which consists in merging tuples that represent the same entity, possibly having different values in the same attribute, like in the example shown below with Tom Hanks and T. Hanks. To perform entity resolution, we use an algorithm similar to what we employ in the schema matching case, which is briefly described here and more thoroughly in the full paper. For each record ID Ri, we find its closest neighbor Rt. If the closest point to Rt is Ri, then they are in match. This is quite a simple symmetric relationship, but it's still effective thanks to the high quality of the embeddings. To conduct the experiment, we gathered a number of datasets from the sources reported at the bottom of the slide. We also constructed the IMDb movie lens dataset starting from open data. The highlighted cells are meant to show the wide range in sizes and percentage of overlapping values. Indeed, MD is very robust to those statistics and can perform well even when the overlap is quite small. In our experimental campaign, we tested 5 different methods. Basic denotes a simple value of word approach in which the corpus is constructed locally by using permutation of tuples. Pre-train describes the case in which we consider embeddings constructed using the pre-computed fast text model with RIDs built by averaging the vectors of each value in a tuple. Both Notovec and HARP are graph embeddings algorithms which generate embeddings starting from the graph we built using the input relation. I would like to point out that it would not be possible to generate the embeddings using these algorithms without a method for translating a table into a graph. For these algorithms, we use the default parameters reported in the original papers. Finally, we test MD using the parameters shown below, unless otherwise indicated. The first results here are those concerning the quality of our embeddings measured according to the test that I've introduced shortly before now. You can see that MD outperforms the other solutions in most cases. In some, basic training shows good results, but has a much larger variance. Red cells denote the runs that failed, either because of memory errors or because the run ran out of time. We do not report here pre-trained results because they are even worse than basic or hard, or they're pretty much useless. For the skill matching case, we tested a simpler situation than the usual, with simple matches and few spurious attributes. This was done as a sanity check for our strategy. The simplicity in our approach can be noticed from the large number of 100% and perfect results all across the board, with Node2Vex still running out of memory. For the MTT resolution situation, we test both supervised and unsupervised cases. The first slide will report the unsupervised results, where you can see that AMD can compete with the state-of-the-art embeddings algorithms, graph embeddings algorithms, and perform much better than pre-trained embeddings on the same task. I highlighted the largest difference between pre-trained and local embeddings to show the advantage yielded by using local embeddings for data integration. For the supervised case, we conducted the experiment by using DPR, which is an existing supervised system for entity resolution, using both pre-trained and local embeddings. It is again possible to see how local embeddings always outperform pre-trained embeddings in the entity resolution task. In this slide, we gather the execution time for the different graph algorithms. In general, AMD is faster than the other approaches. For what concerns future work, we are considering methods for integrating natural language in our pipeline to gather information from more diverse sources. We are also looking into different embeddings algorithms. Finally, we observed that the geometric properties of the embeddings can be used to perform token matching or build a rudimentary query language to produce results like in the example. You see here, Quentin Tarantino plus movie title plus minus director will give us movies by Quentin Tarantino. Here there are a few references, and this is my last slide. So thank you very much for your attention.